I'm a Brunskill. I'm super excited to be here. As Chris mentioned, I'm relatively new faculty to Stanford. I was on faculty at Carnegie Mellon for a while. So you can't see the first slide, so I'll just tell you about it, which is right now, for pretty much everybody in the audience, you've probably heard of some of the amazing success of AI in allowing us to achieve human-level performance on video games, on things like Atari games, which probably some of you guys played in the past, as well as on AlphaGo, which Go is considered one of the hardest board games and is considered a major intellectual achievement for humans. And so it was really quite revolutionary when DeepMind, just a few years ago, showed that we could achieve human-level performance with what's known as reinforcement learning. And so just like some of the advances that Chris was telling you about, there's been a lot of public media about this. It's been an extremely exciting time. But I think if you look at reinforcement learning, which is the technology underlying some of this, its impact on people has been almost zero, I would argue. Unlike deep learning or face recognition, which you probably all have on your smartphone, I don't think many people interact with reinforcement learning agents on a day-to-day level. Now, what is reinforcement learning? Reinforcement learning is this process of learning to help or learning to make decisions through a trial and error process. And so you might wonder if the technology that's being used to try to achieve human-level performance on AlphaGo is really relevant to the types of tasks we might need assistance with. But I'm going to argue to you that it is. So let's look at this example. In this example, we think of a computer trying to help a student learn something. So what the computer can do is it can pick activities, things like videos or ways or problems, present those to a student, and then the student responds in some way. And then the computer has to select the next activity. And then after a little bit of time, it gets some sort of feedback about whether or not it's helping the student learn. So for example, maybe we can see the exam score of a student. Now, in this scenario, this is reinforcement learning because the computer can learn through trial and error to figure out how to best help people learn. And I think that there's not just one example of this, but there are many examples of this, where we'd really like to have these reinforcement learning systems, these continual improvement systems, help figure out what is the right intervention at the right time for whatever objective we're trying to accomplish. And this comes up in lots of things we'd want to do. So I gave you an example with education, but healthcare is another huge example where we're constantly making decisions, and we would love to figure out better decision support to help us make even better decisions. It also comes up in things like e-commerce. When you use Netflix, it is making recommendations, and it is doing so in a way to try to both help you experience content you like and to help them be successful as a business. So I would argue that the reason that we don't see success of reinforcement learning is not because there aren't applications that could really benefit from this sort of technology. I think it is because there's some core limitations to taking what is working well for video games and AlphaGo and using it when we think about these other types of applications. In particular, one of the hard Atari games is called Montezuma's Revenge. It's a challenging game for computers to learn. And what you see on the left here is a number of different rooms that your agent has to navigate through if it's playing this video game. Now, the key thing to look at is at the top, where it says 50 million. So this is showing that after 50 million actions in the game, 50 million time steps of figuring out how to move your joystick, the agent has only managed to go through 2 of this set of rooms. Now, this is just not going to be feasible if we think about trying to use these type of ideas to teach students or help patients or improve things for customers. Similarly, if we look at the performance of these types of systems, they generally are increasing, but it's not monotonic, and it's very noisy. So on the right-hand side here, I'm showing you sort of standard runs of a lot of deep reinforcement learning systems, where they're very, very stochastic. So overall, these systems are improving over time, but they're not necessarily guaranteed to be sort of monotonically improving or doing better and better sequentially. Now, if you're in simulation, this is not a problem. If we're having our AlphaGo game, AlphaGo player play Go in its head for a long period of time, it doesn't matter that its performance is stochastic, as long as when it finally plays a world champion, it does well. But when we think about people, we don't generally have good simulators. So I think one of the core differences when we go from thinking about video games to thinking about people or sustainability or healthcare is that these systems are very hard to simulate. And even if we do have simulations, it's often very costly if you think of something like climate change. And data itself, if we want to run these in the real world, impact real people. So the data is costly, it's really important, and we have bad simulators, which should make you pretty concerned and make you think maybe this is one of the reasons why we haven't seen reinforcement learning systems really impact us in the way that we've seen other deep learning systems. So this is sort of the core foundations of what I think about. I think about how do we have computers that learn how to help people, and they have to reckon with this sort of complexity of these lack of simulators and these high cost. And so in my lab, we're thinking about a bunch of different types of challenges in this area. And today I'll just tell you about a couple of the different ways we're trying to create these sort of systems. And I'm going to start with counterfactual reasoning, because I think that's something which is in some ways a unique benefit to having data that comes from interacting with people or interacting with real systems that we often don't see in video games or robotics. So this issue came up to me first about 5 years ago in a collaboration with my colleague Zoran Popovic over at University of Washington. And in that case, he had this fractions game. He was also very interested in how do we enhance STEM learning for students. And Refraction is a game where students learn about fractions by splitting laser beams. It's been played by approximately 500,000 students. And what we wanted to do is sort of figure out how do we sequence levels and different types of engagement in order to help students learn and persist. So this is an optional learning activity, which means we can't control how long students play it. Students log on, they play it for a while, then they get bored, maybe they go watch Netflix, and we want to figure out how we can help them stay engaged and learning in this activity. So this is a reinforcement learning challenge. We want to figure out how to do adaptive, personalized sequencing for students in a way that's going to help them persist and learn across all the different types of activities that are present in this game. So in other words, we want to learn a decision policy. We want to capture something about the student or player state in order to make good recommendations and good suggestions for what the next thing is that they're going to play. And the key benefit that we have here, that we don't often have for video games or for robotics, is that there are a lot of people playing this game. And so we wanted to see whether or not we could use that old data to figure out how to make good new decisions for future students. And this is known as counterfactual reasoning, or what-if reasoning. And the idea in this case is that we often do have access to large repositories of past data and their decisions, and the outcomes of those decisions. And the question is, how can we use that data in order to make better decisions in the future? So I would argue this is one of sort of the quintessential intellectual questions of our time. Judea Pearl gives a lovely talk where he argues that our ability to think about things that have never happened before is really a quintessential aspect of human intelligence. You know, we can imagine centaurs and other things like that that have never existed before. And so what we want to do in this case is to use our old data to figure out, for example, in the context of healthcare, what might be different, more effective decision policies. Now, this is a hard problem, and it's different than supervised learning for a number of reasons, but perhaps the most critical one is that the data is censored. You could never know what it would have been like if you skipped this symposium this morning and went to your favorite coffee house. And so data is inherently, compared to supervised learning where you get labels, here you only get labels for things you try. So that incurs a very big challenge when we're trying to use that data to figure out what we should do in the future. The other is that particularly when we're thinking of sequences of decisions, we have to do something smart about generalization. The combinatorics of the different types of activities we could take and in what order grow exponentially with the number of time steps. So we have to be able to use our old data in a careful way so that we don't incur that combinatorial explosion. So in this particular example, the data that we had access to was from about 11,000 students that had previously played the game. And in this case, what we had done is we had randomly ordered the levels. So we gave people different levels, and the levels here really you can think of as just sort of different ways of playing the game. They might encode different types of concepts. Some might be harder than others. Some might merely be different. And we didn't have great intuition of what order we should do these in. Now, to be clear, before we had sort of like an expert person design a particular sequence that most students were getting, but we decided to experiment on this fraction of the data, on the fraction of the students that were playing it in this condition, so that we could get an idea of whether or not we might be able to do better. So the third thing that you might think of doing, and that we thought of doing, is that maybe we could build some sort of machine learning model to predict player behavior. So we're going to take all of our old data, we're going to build a predictive simulator, essentially, so that we can simulate what might happen if we were to to introduce different types of levels to the student. And the nice thing is that once we have this simulator, now we're kind of back in the same land that we were in video games, because we can use that simulator as a fake student and then try to optimize for the fake student. Now, as you might imagine, if the model of the learner is bad, like if you have a bad simulator, your decision policy might be poor. So if my fake student isn't a really good replica of real students, if I optimize for my fake student, the types of activities I take may not be very reflective of what actually is helpful for real students. So we sort of expected that might happen. The thing we didn't expect was the following. So what this graph is showing is a measure of complexity of the student model on the bottom. Now these are all pretty simple student models, but essentially the complexity of how we're capturing student state is increasing on the x-axis. And on the y-axis, we're looking at two different forms of fit. The first is the gray line, which you can see is just going up and up. And that is, how good is this model at predicting student player performance? And you can see as you use a more complex model of student learning, we're just getting better fit. This is in a held out set, so this is not due to overfitting. But the important thing to notice is the black line. The black line is if we take these models and then try to optimize for them, and then we run those real policies out, and how well do they do? And what you can see here is that actually a much simpler model of student learning is getting much better performance in terms of the criteria we really care about, which is student engagement, compared to our ability to predict student performance. And I think this is really important because what this suggests is that the models that allow us to predict behavior may not always be the same models that are good for optimizing for the objectives we care about. And if we really care about the final objectives, like student learning or patient outcomes, we need to make sure that our models are actually allowing us to capture and enable us to achieve those goals. So one of the challenges and why these occur is that in these cases, the models are all somewhat limited, and there's statistical bias in the model, which means that even asymptotically, if we had a lot of data, we would never get the right answer, and we would never be able to optimize correctly. So based on this, we took a different approach. In this case, we decided to instead use importance sampling, which allows us to get unbiased estimators. So we said, instead of trying to directly model player performance, we're instead going to use importance sampling. And when we do this, we're going to be able to directly get an estimate of how good this policy is. Now, the nice thing about doing this is it allows us to evaluate lots of different ways of trying to engage with students. So it's not particularly important to look at the x-axis here, except for to notice that we tried lots of different policies and representations, and we could fairly evaluate each of them using this using importance sampling. And the encouraging thing we saw is that we did identify, now this is all just on our old data, we identified one policy that we thought would substantially improve engagement. So we thought that we could increase persistence by around 30%, compared to a baseline of just showing things in random order. Now, the other important thing to notice is on the left-hand side here, which is the current expert policy. Now, you notice that this goes in the opposite direction, which indicates that we estimated that the current expert performance is actually worse than just randomly showing things to students. Now, obviously, that's a little bit unfortunate because you would like to believe that your human experts are at least better than random. But I think actually this shows the power of reinforcement learning for some of these really complex tasks where we don't always have good intuition of how to actually sequence activities in a way that's effective. Now, this is all just predicted improvement. The critical question is, does this actually reflect real, how students would really do if we run this in practice? So what we did is we took around 2,000 additional learners, and we tried to see whether or not these policies we'd identified were really better in practice. Now remember, we're predicting about 30% improvement, and what we found is that we actually got an improvement around 32%. So I was really excited when I saw this because it meant that not only were we getting something that substantially improved persistence, but that we could predict this in advance. So I think the really powerful thing is both that reinforcement learning can allow us to identify sometimes substantially better strategies using old data, and that we can understand how good those strategies are before we actually deploy them, which I think is really important for high-stakes domains. Now, we're doing a number of additional extensions to this. There's still a number of challenges. One of the things that we found initially is that this alternative approach works well if you're only making a small number of decisions, but if you have interactions that go on for a sustained period of time, imagine that you're Amazon and you're dealing with customers that you're hopefully interacting with across weeks or months, that this type of importance sampling method ends up having a prohibitive amount of variance. So doubly robust methods that come from statistics allow us to combine models that typically have some amount of bias but low variance with importance sampling methods which have high variance and low bias. So by combining these two together and trying to directly optimize for mean squared error, we can get substantially better estimators. And this is for a small illustrative example, but we found in this case, so here the y-axis is log scale and the x-axis is data. And what we can see is that we're getting substantially better mean squared error, so lower is better, by using these sort of doubly robust estimators. Now, I think that's one way to look at it, but I think what's more powerful is to think about it in terms of this, which is that for the same amount of, to get the same amount of accuracy to predict how well you're gonna do, you might need roughly an order of magnitude less data. Now, this is important because if we're doing this for some conditions where there aren't a lot of people, or if you want to, as quickly as possible, be able to make better decisions for people, we want to minimize the amount of data we need in order to start to make smarter decisions. So that's where these sort of estimators and being more statistically efficient can be really powerful. Now, I said before that we found this weird issue that if you have the statistical bias in your model, that even models that are looking better may actually be worse when you start to optimize. But when we were revisiting this, we started to revisit this about a year or two ago, because we've been seeing with deep neural networks that these models have amazing expressive power. And so we thought, well, maybe we should revisit to see whether or not we can leverage some of the deep learning models to re-tackle this problem. And in particular, maybe models aren't always bad, but perhaps we were using the wrong model class, and maybe the way we were trying to fit these models wasn't very good. And so we had a recent paper at NeurIPS looking at trying to fit different types of models using different types of loss functions. And we're particularly interested in this for healthcare data. So the idea was, can we now use deep neural networks to do this sort of build counterfactual models that we can use to optimize and make better decisions? And one of the nice things that when we were doing this is that we found that we could use different types of loss functions that are sort of encoding the idea of fine-tuning that we see often in deep learning, but now we're kind of fine-tuning across different types of policies, and that it's also allowing us to tackle a lot of problems that come up in practice. So for example, in healthcare, often we have observational data, which means that we don't have direct access to what was the policy used by the clinician. When a clinician makes a decision, they don't always write out, this was my probability distribution over what treatment plan I was going to use. And so we have to infer that from data. And so using this method also allowed us to tackle a lot of different issues that we see commonly coming up there, including the fact that we want to be able to make estimates of how good our new policies are, not just in aggregate, but for individuals, so that I can say, for this particular patient, how well do I think this treatment strategy is going to do? So I think there's a tremendous opportunity right now to think about counterfactual reasoning and reinforcement learning together. I've been increasingly excited as I've been talking to different companies about how many people in Silicon Valley are also thinking about this agenda right now, because I think that there's the chance now as we have so many systems that are interacting with people over time and gathering this data to do a better job at using that data so that we can make better decisions for all the people that these systems are interacting with. Now, I want to talk next about another aspect that we're tackling in this lab, which has to do with the fact that, of course, in machine learning, we're not just thinking about systems that statically have data, but we're thinking about systems that improve. And I think there's this wonderful quote by Tom Mitchell, who's the I think current dean at CMU, which argues that the foundations of what machine learning means is that a computer system that improves as it gets more experience. And I think that's one of the core differences between reinforcement learning versus economics and statistics, is that in AI we think deeply about how can this system actively improve over time. And so when we talk about systems that learn to help by trial and error, that often seems to imply that these systems are just sort of randomly making decisions. But we want to do much better than that, and we need to do much better than that if we want these systems to quickly learn to make good decisions. Now, again, if we think about sort of what is perhaps the most common mode of systems that are actively improving, is what they do is they look at sort of what has worked well in the past, on average, and they mostly do that plus a little bit of randomization. So a lot of the success in video games for Atari actually can work with this sort of fundamental principle. But one of the challenges is that that can work asymptotically, but they tend to improve really slowly. So if we think about these systems now interacting with people, you might get a trajectory that looks like the following, where we think of sort of the score for each person, perhaps that's how well students are doing on a test, and over time it's slowly going up, but it's not going up very quickly. So I think that we can do much better than that, and an alternative is to think about kind of all the worlds that are consistent with the data that you observe. So instead of just averaging your prior experience, you can think about all the parameters that could have generated that prior experience. And then it turns out a key principle here is to be optimistic. And I love that idea. So the idea in this case is to take all the possible worlds that we have and then to be optimistic under what is the best possible world that could have generated the data that you've observed so far, and use that to try to figure out how to act in the future. Now, optimism turns out to be really powerful for two reasons. The first is, if you're really optimistic, one possibility is that you're right. The world really is fabulous. And in which case, if you take those decisions, the world will be terrific, and you'll get really high rewards and outcomes. So that's one possibility for optimism, and of course, if that happens, things are great. But the other possibility is that, sadly, your algorithm is diluted, the world is not really that good, but in that case, we learn something. So if we try to do something and it turns out that the world isn't as good as what we hoped it would be, isn't as effective at teaching students as we expected, we're going to get corrective feedback. And once we have that corrective feedback, we can update our models, and now we'll be a little bit more realistic about the outcomes. And so then we'll learn and be able to quickly converge to the types of decisions we want to make. And so optimism under uncertainty allows us to have algorithms that learn much more strategically and quickly, because they are optimistic, either they do well or they learn something quickly that shows them that they need to be more realistic in that expectation and take a different decision. And in fact, one of the things that I think is really beautiful that we've been finding over the last few years is that we're really starting to define the boundaries of what it means for any agent to learn efficiently. And we're defining this both for the worst case scenario as well as in problem-dependent settings. When I say problem-dependent settings, I mean the fact that in many real-world cases, fortunately, they're much better than the hardest cases, and so we can explicitly learn how hard it might be to make good decisions if there's structure in the domain. And so, in fact, one of the beautiful things of optimism is that it is provably optimal, meaning that we have tight upper and lower bounds for how good we can do in some of these scenarios. Now, just before I close, I want to talk about another core aspect of this, which is all of this work that we do, and a bunch of it is algorithmic and theoretical, is really focused around the idea of how do we support people in their own goals. So who here has seen The Matrix? Okay, a number of people, but not everybody. So The Matrix, to me, is a beautiful example of technology augmenting and aiding people. In this particular example, there's a main character called Trinity, and she needs to learn how to fly a helicopter because the bad guys are coming. And so what she does is she calls up and she says, please download a program into my brain that will help me fly this helicopter. So they download a program into her brain, and about 30 seconds later, she can go off and she can save the world. Now, this is a wonderful example of technology aiding someone in exactly the goals they want to do. And I think that that's the vision that I and many, many others are working towards. But there's another recent movie, a more recent movie, that perhaps has a more cautionary note. And this is WALL-E. And if you watch the movie WALL-E, it provides a much more sobering idea of what technology might do to us, and that it might, in fact, cripple our capabilities instead of enhancing it. And so I think when we consider agents that are sort of learning to help or agents that are optimizing for a goal, we want to think really deeply about what is the goal or the reward function we're optimizing for. And we often don't know exactly what that should be, and that typically comes from domain experts. So in my own work, we think a lot about doing this in the context of education and training. And so we explore different types of goals, things like how do we reach the same stage faster? So how can you learn the same amount of material faster in Korean language learning? In this context, I talked before about how we can have students persist for longer. Or how can we help students learn to be much more engaged and actually learn more material because they are more engaged in these types of interventions? But I think the thing that I am most excited about going forward is the idea of bringing together machines and people so that they can be more than the sum of their parts. And I'll give you a brief example of that. So one thing I would love to have is to enable all novices to be experts from day one. And I think in many cases we can start to achieve that with AI support and assistance. But again, if we want this AI support and assistance to ultimately be an amplifier instead of a crutch, I think we want to transition between performance support to learning support. And so we're looking at that in my lab so that we can figure out how can we both help people from the beginning, but allow them eventually to become the master. And I think if we can do this, we will ultimately achieve unimaginable benefits. Thank you.
Thank you, Emma. I think we have some time for a couple questions. We have microphones in the back two corners and then up here too. So please try to make sure you use the mic and let me know if you have questions. So I can start with a question, actually. Considering a lot of the people in the company are corporate members, and considering this is, a very broad, ambitious goal, I think my question is, what can corporate members at Stanford do to help you achieve your goals and help, create and advance the field of reinforcement learning and make it, much more applied and implementable in industry?
Thanks for the question. I think that there's a couple things that I think are really exciting about partnerships between academia and industry along this type of frontier. One is that I think that there's a lot of real opportunity to collaborate around both sort of using existing data sets to figure out how to make better decisions, but also to better understand the circumstances that are coming up in companies in terms of some of the different challenges. So I can give an example. So you might imagine in some scenarios that it's easier if you're a company that's serving material because you understand exactly who gets served what. But in fact, there are lots of other reasons why, an email you sent out might go to someone's spam filter, and it may go to someone's spam filter in a way that's not random. So it might mean that particular demographics of users are not receiving your interventions. Similarly, in the type of work that we're doing on sort of safety and equity, you may want to make sure that there's sort of a minimal level performance for all of your customers and to be able to guarantee that. So I think those are the sorts of areas and questions that can mean that both push the research frontier as well as can be really productive forms of collaboration.
Nice talk to kick the day off. I'm Ted Goldstein from Anthem Health Insurance. And in healthcare, of course, we're faced with a lot of decisions, and the policy in a lot of medical applications is to be pessimistic. Right? So, for example, imagine we're trying to determine the optimal length of time to be on cancer therapy, right? And of course, cancer therapy is very difficult on the patient, it's expensive and such, but you want to eradicate the cancer, right? So, the cancer, a very typical thing is that the disease is not detectable after 6 or 8 weeks of therapy, but we're going to leave them on the patient for 6 months. Right, because we want to make absolutely sure, and so I'm thinking about your optimism assumption, right, about things, and is that applicable here, right? In other words, have you tried to reverse the sign of your your assumption there, and how bad is it, right? And how do we actually find the right decision boundary so that, we have greater confidence, right? Obviously, you could take chemotherapy forever, the rest of your life, and that would be, the most pessimistic assumption. So we're clearly not at the most pessimistic assumption, but we're making pretty pessimistic assumptions about these things.
Yeah, I think that's a great question. So I guess one of the things I want to clarify is when I say in being optimism, I think when you're doing online, it can be helpful, but the objective itself matters. So I think in that case, I would argue that you're optimizing for a risk-sensitive measure. So instead of looking at expected outcome, you're looking at something like conditional value at risk or some sort of other sort of tail distribution. And so actually one of the things we've been working on very recently over the last year is looking at how can we quickly find risk-sensitive policies. So let's say you want to optimize for the 5% worst outcome. How can we quickly find those sorts of strategies? Because I completely agree. In many cases, you don't care about, on average, what the customer experience or the patient or the student experience. You want to make sure that sort of no one's left behind and that the experience is good for everyone or some minimum guarantees. And so we've been doing active work on that area.
One more question.
This is Yifeng from Lam Research. We are in semiconductor industry. So it's kind of similar to the healthcare industry. I wonder, how do you handle the discounted reward in the future? Typically in reinforcement learning, in a simulator environment, you can account for those. But in reality, either in healthcare or in our semiconductor manufacturing, it's really hard to model those.
I think the issue of discount is a really interesting one. We typically often introduce discount for one of two reasons, either for mathematical convenience, which is not a very good justification, or because we think that models how people really think about risk and reward. So I think in some of these cases, you can just directly not have a discount factor and you have a fixed horizon you're optimizing over, like the next 5 quarters or the next 2 years. And in other cases, you can use sort of different rolling horizons, like receding horizon control, where you're always thinking 5 steps ahead, and then you take a step and then you think another 5 steps ahead. So I think we can account for those different forms of horizons of decision making.
Thank you very much, Professor Brunskill.